Good morning. It's an honor to be here, albeit virtually. But to begin, I would like to thank the ECOC Selection Committee for inviting me to speak on this topic, emerging industrial manufacturing requirements. We're going to be discussing digital twins, industrial IoT devices, 5G networks for connectivity and security. So without further ado, let me share my screen. Go. There. Okay. So I'm Tracey Vanik. I'm the head of Photonics Market Research at EPIC. That's the European Photonics Industrial Consortium. And very pleased to be here discussing digital twins, industrial IoT sensors, 5G, and security. So what we're going to cover includes not only digital twinning, but imaging for manufacturing and bandwidth that is required in order to support Industry 4.0, as well as these manufacturing operations. We'll look at timing considerations, which are always of importance within manufacturing, as well as security for the manufacturing process itself. So to begin, what's a digital twin? This is a term that's been used for quite a while, and it means many things, which has led to a bit of confusion. But basically, it's a software model, and it can be a software model of many different things. It can be a software model of a component, of a device, of a system. It can be a software model of a building or of a robotic operation, or it can be a model of how you expect something to operate. So a digital twin can be many things, but it's basically a digital prototype of, for us, a product, a software representation of an object that receives information from sensors. And it's so much more than early CAD/CAM software, for those of you who remember this. That was a computer-aided design and computer-aided manufacturing. Instead, digital twins represent dynamic, up-to-date representation of what you're manufacturing. It's real-time information that is compared against your model. And the current software that you can purchase, depending upon what you choose to select, can include many simulation options, can give you error correction, can provide analysis of different materials, and it can even help compensate for aging manufacturing equipment or identify material differences. Let me get my pointer started here. Come on, there we go. There, okay. So a digital twin gives you the potential for continuous optimization. It can provide increases in efficiency and increases in precision. And all of this results in reduced yields, which reduces your costs and improves your quality of your manufacturing. Additionally, digital twins can provide critical remote process monitoring and predictive maintenance so that you know how well your systems are functioning, and you can actually take preventative measures so that you can repair rather than replace either a device or a manufactured product. So the consideration is that digital twinning requires very high bandwidth utilization in order to share this information. Now, let's take a look at something at specialized system control, localized system control, and process manufacturing control. So in this case, we have a Precitet laser system that provides continuous information about the quality of its laser beam and lasing service. So you have continuous monitoring, you have a camera for this, you can control the power of the laser and the focusing. All of this is possible through this localized feedback of the system. But in addition to this, the Precitet system also supports feedback to manufacturing process control, so that process control can be monitoring what is happening to the operation of this laser and these laser component systems over time. Are we starting to see degradation? How does the product look? Are the products consistently meeting the goals? So now you have a combination of both localized and centralized process information. And there are other ways to do this. So in addition to using a camera, you can use something relatively new, digital holographic microscopy, or DHM. DHM provides feedback for precision micromachining, for femtosecond laser engraving, so it's precise that it can provide measurements of phase patterns that are used during the engraving process. And DHM can be leveraged to control not to provide not just the feedback on what's happening, but to actually control the laser beam parameters. So as you can imagine, data is going to drive these digital twins. You need to be able to take an image or provide information about the product that you are currently manufacturing at that moment and send it back to manufacturing control. So mission control in a sense. So in this case, we have an automation technology, an IRSX, smart infrared camera with measurements. So here's the camera. This is the image of the object that was being created. And you see that the camera is connected through a network. It's connected through, in this case, an Ethernet network. It doesn't have to be Ethernet, but it's connected to a network. So it can share information with SCADA, with process control, as well as with specialized servers that are used to monitor alarms, or with simulation software, basically the digital twin software. So the potential drawback, though, is that here you're taking real-time images, and you're taking a lot of them. And this information is going to deluge the network. So how do you handle this? Well, we'll talk about that later. But right now, there are other vision technologies that can be employed, so or deployed, as the case may be. So we've seen camera systems, so visible. We can look at multispectral imaging, infrared, shortwave, long wave. We can look at a 3D profile or a point cloud or a 3D snapshot, or acoustic imaging with ultrasound. There are a number of different ways that we can visualize how our product is being made. So one of the interesting ones to me is hyperspectral imaging. Hyperspectral imaging can identify materials within a product. So this can be extremely important for pharmaceutical manufacturing as well as for foodstuffs. So for example, here we have what looks like all white tablets. Some of them are a different size, but we have a mixture of tablets that would be difficult to sort to the human eye. But by using hyperspectral imaging, we know what the composition is of those tablets, and we can identify that very rapidly. And here, this would be, at least to me, a challenge, a problem, because you're taking all of these different materials and loading them into one bottle. So this can help you prevent some critical errors for manufacturing of pharmaceuticals. When we think of digital twins, we normally think of it making a product, but a digital twin can also be used for robotic control. So one of the things that robots can be used for, in addition to actual manufacturing process, but they can be used for inspection. And they can inspect every assembly. Now, this used to be done by humans, but humans were not fast enough to be able to inspect every assembly, to be able to inspect a high number of inspection points, and to record the results, either on a tablet or a flip chart. But with digital twinning, the robot can provide that operation and can send those recorded results back to the manufacturing operation. So they're automatically recorded. And the results of this are really quite amazing. Not only do these robots meet the overall cycle time, even while inspecting more areas of the parts, but they provided cost savings and quality improvements. And those savings were able to pay for a robot within 4 months. Now, the other thing that we can do is we can use 3D LiDAR as a means of tracking our robots. So robots on the manufacturing floor are often used as a means of providing materials needed for manufacturing. So, but you don't want those materials to be late because it can hold up the production line. So you can use 3D LiDAR as a means of tracking the robots, tracking their movements, seeing if there's any variance, and also providing velocity vector estimates so that if something is late, when will it be there? As well as providing information on collision or being able to predict potential collisions on the floor. Now, you've heard of autonomous vehicles. Well, did you know that there are autonomous robots at this point? So now you can have robots that are self-driving, that are under their own control scheme. So, but one of the things that enables this is a very good imaging. So being able to create a point cloud of their environment so that they know where the objects are that they're looking for, so they know what objects to avoid. And so you have the ability to for the robot to control its own environment and to monitor what is happening in the environment, even if it changes. So in this case, this is the Jabil, the omnidirectional sensor. You can use one of these instead of multiples around the robot. And this one sensor will provide you with a wider field of view. And in addition to this, it also takes and reports that information back to the automated system control. So this way you have information about what is going on with that robot, and you can do a deeper drill should you need to find out what has happened to a particular system. So when we talk about providing images and sensors and being able to control what's happening on the floor, this requires bandwidth. How are you going to do that? Let's first take a look at Industry 4.0. The goal of Industry 4.0 is to provide safer and more efficient factories by enabling better automation with better insights from data and analysis, with improved operational efficiencies, being able to support devices communicating directly between one another instead of communicating back to a router and then back to a different device. And it provides more information on processes and helps make the environmental, the manufacturing environment safer for humans, so that humans no longer need to be exposed to corrosive materials or dangerous situations. In addition, this Industry 4.0 can provide precision, repeated, difficult work that would tend to see fatigue with a human. These rely upon intelligence from manufacturing equipment. By intelligence, I mean things like machine learning, neural networks, or artificial intelligence. Sometimes machine learning with a repetitive pattern is enough. So to get these improved efficiencies, though, you need to be able to communicate. And how do you do that? And 5G has emerged as one of the best means of being able to support this increased connectivity to support Industry 4.0. And the way that it does it is it's wireless, so there's no cables. And a manufacturing floor traditionally is very messy and also dangerous because of the cables, very easy to trip. And you also need to have bandwidth availability. There's plenty of bandwidth available on 5G. And it also supports faster communication, which is needed for real-time manufacturing data. And it can connect not just PCs, but it can connect processes, industrial IoT sensors and videos, and robots. And this in turn provides improved detection of timing inefficiencies, which result in reduced yields, not in time materials, or degradation of equipment manufacturing that can result in either the line being stopped or hopefully identifying that degradation so that you can repair it before catastrophic failure. So let's look at a private 5G. Now, when we think of 5G network that we have on our cell phone, that's a ubiquitous network that connects all of us to our carriers, whatever the carrier happens to be. But in a private 5G network, in this case, the floor would have its own antennas and its own 5G network that is not shared with the outside world. That's a good thing. But you'll notice that in this case, there's no segmentation. It's a flat network. We'll talk about that more later. So these little blue dots, these represent antennas. In this case, these are MIMO antennas, massive input, massive output antennas. Can be 4x4 elements or 64x64 or even larger. But for this, you can probably get away with something smaller. And the advantage is that it does not need to be mounted onto a large antenna mount. And all of these communications, all of these antennas in turn communicate back to the 5G core network that is owned by the company, or perhaps leased from the carrier. But one of the things with that network is it was not segmented. So you had the potential where, since it was flat, that if there should be malware that entered that network, it had the potential to infect every device. So one really basic thing that can help protect a manufacturing environment is a firewall in front of each one of the segments so that you're protecting individual robots and you don't have the chance of of your whole robot manufacturing stream being infected. So you can use private 5G or you can use millimeter wave. Now, 5G is a sub-gigahertz bandwidth, whereas millimeter wave is higher frequencies. So these higher frequencies translate to higher bandwidth, lower latency, but because they're higher frequency, there's more loss with distance, so they cover shorter distances. So you may need to have more of these than a standard 5G antenna. But it's entering the market for manufacturing sites. So there's the first 5G millimeter wave smart factory in Taiwan. And also, there's another first smart factory in China. So they're really gathering steam. They're gathering momentum. And part of it is that we're seeing some smaller deployable antennas that can be used not only for millimeter wave, but for 5G as well. Now, when we talk about 5G, one of the key functions of 5G and the key requirement is timing. And timing is also critical for industrial applications. Industrial 4.0 communications, in fact, require tight timing and sync for maximum yields. For optimal production efficiency, in fact, all of the equipment must be very carefully orchestrated. And time-sensitive networks help enable this, and as well as other applications that require tight synchronization, including 5G. So precise time synchronization is required throughout the network, including devices. Why is this important for industrial manufacturing? It's important because it relates to money. So when you look at manufacturing, you want everything to be orchestrated together so that the product of one process that is required for the next is presented in time, on time, and that the maximum yields are dependent upon this dependency so that there is no delay in the manufacturing process, because delays translate to reduced revenue. So you want to have more saleable products, and more saleable products translates to increased revenue. Now, this slide is more of a reference, but it's we're not going to go through the protocols. But for a timing network, especially for 5G and for Industrial 4.0, you need to have a centralized timing source. What is your source of synchronization? Typically, it's GNSS. It can also be a core timing network that utilizes a GNSS offset that distributes that timing and synchronization throughout the network so that the entire network shares a common base, shares a common synchronization and the common timing base from the switches and routers that would be used to the front haul network to the antennas. And why is this important? It's because 5G is operating at much higher frequencies and as a result at much higher data rates. And so there are more stringent timing requirements. And there needs to be a common timing base for all devices that are communicated on that network. And that means that it's essential for all manufacturing equipment. I mentioned that the area of concern was this flat architecture. You see that everything connects to everything else. Well, this actually represents different network approaches. It's almost a religion. When you think about a formal enterprise network, say that you're a mid-sized company and you have your network in your office to connect all of your workers and maybe a few other things, or a large company, or even a small startup. You have a small network that is used to share common items such as servers and printers. So this is very common for the enterprise. You have user identification in the form of login credentials. You have permissions that are created for different access levels, whether it's your engineering systems. Not everyone needs to have access to those. Whether it's your sales information, not everyone should have access to those. So you can create permissions of who is allowed to access and modify that data. And then in addition to that, on a LAN network, you typically have firewalls, as well as possibly intrusion protection or prevention systems. And you may even monitor traffic heuristics to detect abnormal traffic patterns that might indicate that you have someone that is not supposed to be there on your network. But contrast that with a telephone network. The WAN, in this case, it's a different philosophy. It's a flat network. It's a ubiquitous network, and everyone connects to this carrier that they've subscribed to. Permissions? No, it's not permissions. It's billing. So billing takes the place of permissions. And here you're looking for any additional things that can be billed, whether it's long distance or message rates, et cetera. The security systems tend to be carrier-based, although you may have some users that actually install anti-malware for the phones. Strongly recommended. Now, what about for 5G and industrial manufacturing? Well, here, the security of the processes is paramount, because those processes not only represent your product, not only represent your revenue, but it also represents an incredible investment. So the process control equipment must be protected, and all process activities also must be protected. So how do you do this, and do you care? Okay, so process control network segmentation for safety. Now, if you are a large manufacturer, you care about this information. If you are a small sensor manufacturer, you may not care about this information directly, but it's helpful to be aware of it. So looking at segmentation for safety, you're looking at the enterprise side, where you have general workers that are not involved in production. That's considered the evil side of the network, because an employee can take home their laptop, their 10-year-old can get a hold of that laptop and download a really cool game that happens to be full of malware. And then when the employee brings it back into the office the next day, the office is infected. So we want to be sure that we have very stringent firewalls between the enterprise side of the house and the manufacturing side of the house. So the strongest firewall is called the DMZ, or the demilitarized zone. And then you have different levels of operation that are all segmented and protected, from the process equipment, which is where you have significant investment in materials and equipment, to the control of that equipment, to the supervisory control of multiple processes, and then finally to the manufacturing operations and control. This is where your point clouds report to. This is where your sensors report to. So you have to get all that sensor information down here from process equipment and possibly process control. It has to make its way up to manufacturing operations and control. Now, but to do that, there may be some delays, because you have to pass through firewalls and there may be some processes. But these segmentations are important in order to protect the network. So how do you get those small messages up to where they need to be seen? Well, first of all, some generalizations on industrial IoT message. And here I use IoT, but I'm referring to industrial IoT. Keep in mind that information from small sensors, trackers, wearables, these are all tiny messages. It's basically a header, a footer, and a small word. Cameras and videos, however, represent much larger images. So not all IoT sensors generate tons of traffic. But for manufacturing, you can have a mixture of message sizes as well as some that are time sensitive. So if you have an error message, if you are looking at providing real-time quality information, all of this is time sensitive. And you want to be sure that you're able to pass that information up correctly. So how does someone who is implementing manufacturing deploy your IoT sensors? Well, they may deploy your IoT sensors directly with the process equipment or process control, and it's part of this segmented architecture. But they may also choose to deploy it in a slightly different manner, because you want to be sure that time-sensitive messages can make it up to manufacturing operations and control quickly, that your videos, that your images also make it up there in real time. So you want this real-time information to pass. So one thing that might be done is your manufacturing floor may choose to deploy a data dial, which allows for one-way communication from the IoT sensor up to manufacturing operations and control. Now here you still have the potential vulnerability of this being a highway for a potential breach, but this helps protect ingress of bad data into the process of equipment. So no one wants their sensor or their company name to be associated with a critical event. So you can't control how your IoT device is deployed, but what you can control is the security for the IoT device. So providing IoT device security, what do? Well, it's actually kind of easy. You get a chip. You incorporate a security chip, and yes, it's going to increase your bill of materials. However, now your IoT sensor can be sold as a security-enabled sensor. But you want to consider who your customer is. So if you're selling to a large automobile manufacturer or a pharmaceutical, you're going to want to have security incorporated into your IoT sensor. If you're selling into prototype shops, arguably not. So consider who your customer is. And then what to look for. You want to be sure that every IoT device has a unique identification, that it offers encryption, data protection, that it can be updated with software and firmware, and that it logs any security events. But one of the more interesting applications is something called PUF. PUF is physically unclonable function. Every IC is different in unpredictable, minute ways as an unavoidable side effect of manufacturing. And it's unique for each device, and it's stable over time, and it cannot be observed from a network. So a PUF-based key does not exist in memory. It's integrated. It's something that it is. And so potential to build PUFs can be made with very small hardware investment. Matson Integrated has done a great deal of work on this, but it's not alone. And there are also emerging optical PUFs that are being created that utilize a random optical multiple scattering medium, which serves as a token. So either using industrial IoT devices or using PUF, this can help protect your IoT device and help prevent you from being named as the source of a breach. Okay, with that, we have covered digital twins, imaging for manufacturing, how do you supply the bandwidth? We've talked about that, and 5G networks and Industry 4.0. Timing considerations, where time is money, and security for industrial manufacturing processes. And I think we made it at 25 minutes, so thank you so much. And this is from EPIC, European Photonics Industry Consortium, over 700 member companies from startups to large multinationals. We look at materials, components, solutions, systems, and we have 5 employees that hold the doctorates. Our technology focuses a wide range from lasers to quantum technologies to PICs and spectroscopy and even 5G. And we conduct online technology meetings routinely, courtesy of our wonderful CTO, Jose Poto, and we also help you connect with other members up and down the supply chain to help enable your product development. And with that, I would like to thank you so much for your attention. And if you have any questions, please feel free to contact me at tracy.vanik@epic-association.com. Thank you so much.